comment if I'm completely visible or not. Anyone in the comment section, please. Okay, so we were doing advanced data structures. Okay, so let us do a small recap. Okay, so let us do a small recap what we have studied in this series. So we have discussed the prefix structure, both 1D plus 2D. We have discussed about the difference array. For updates, that is for range updates. Please anyone write if I am like audible to anyone. Am I completely audible? Please write in chat box. Okay. So and the third thing we have done is square root decomposition. Okay, and now we are going to study an algorithm. Okay, someone has mentioned like yes, I am audible. Okay, so now we are going to talk about an algorithm that is based on the idea of the square root decomposition. So that algorithm is Mohs algorithm. Okay, so our topic today is Mohs algorithm. Okay, so before starting with the Mohs algorithm, first we have to we have to have a complete idea of the square root decomposition. So let me take a recap of the square root decomposition, what we were doing in the square root decomposition. Okay, so in the square root decomposition, what we were doing, we are having an array. Okay, and we are having an array and we are given some kind of queries. Okay, and these queries are like query say QUE query L to R. Now we are asked to do some operations on this range, for this range, that is L to R. So suppose we can be asked to find sum of L to R like this. Okay, and the other query we are given is say update query at index IND say a value x. So you would be having something at your index already and you have to update it by a value of x. Okay, now suppose if the value y is written over at the index I and d, then if you are updating it with the x, you are changing the sum by x minus y. Okay, so this is what you have to do in the query, and this is what you have to do in the updates. So in the naive way, we were traversing the whole array, so that is not efficient. So what we have done, we have like divided the complete array into the smaller number of chunks, and then we have stored the result of each query for all the elements that falls in a particular chunk. So for that we have stored the result, and then if we are given some query like L to R, then what we were doing, we are first checking all the chunks that completely falls into this range, and then we have calculated the result for them, and then we would be having some left out elements, the individual elements, and we are calculating the results for them manually. Okay, so this is what we are doing in the square root decomposition technique. So this is just the idea. We are not going to use the square root decomposition directly in our problems because it is not that efficient. And what we were doing, like, this is a direct idea, we are not going to get questions on that idea, but this idea is used to implement an algorithm that is called as the Mohs algorithm, and we are definitely going to get a lots of problems on the Mohs algorithm. Okay, so one thing to note that okay, so one thing to note is we are having what we were doing in the square root decomposition was online queries. Okay, so here we are processing the queries online. Like we are given, like if one is the type of query in which we have to calculate the sum of L to R, and the two is the type of query in which we have to do the updation. So we can get any sequence of operations. Like if we are given say 5 queries, we can get two one queries, then then a query of type 2, then again a query of type 2, then again a query of type 1. So we can get any sequence of these type of queries. So this is nothing but the online queries. So what the online query means, we have to process the previous query before processing this I query. Like suppose if we are processing the I query, then we have to, like, at this point we must have calculated the result for I minus 1th query. Okay, so this is what the online query means. But now the algorithm we are going to discuss deals with the offline queries. Okay, so the first thing we must note about the Mohs algorithm. Okay, so the first thing, it is only applicable on offline queries. Okay, so if we are going to get a problem, and if we are able to categorize the queries, the kind of problem. Okay, like if we are getting a problem and in the problem we are asked some number of queries, and if we are able to say identify the nature of the queries, like if we can categorize it as offline, if we are able to identify that, then only we can apply the Mohs algorithm here. Otherwise it would be difficult to do so. Okay, now, so the first thing is the nature of query, that is offline. Okay, so this is one thing to note, and so this is the first thing. And the second thing to note is it is using the square root decomposition technique. The idea behind that is the square root decomposition. And third thing is maintaining a data structure. Maintaining a data structure. Okay, so the third thing is maintaining a data structure. So we would be maintaining a data structure, and what kind of data structure we are going to maintain and what it is doing, we would be discussing that later. But first let us take a overview of the algorithm. Okay, so what we are doing in the maintaining a data structure, we have to, like, in our data structure we have to implement two operations. One is the remove and the another one is add. Okay, so what this remove and add operations would be doing, so add would be adding an element in the range and remove would be deleting an element from the range, and these two must be efficient. Okay, so we have to choose our data structure so that in such a way that we can implement these two operations. Okay, so like if we are able to implement these two operations efficiently, we can definitely apply the Mohs algorithm. Okay, now what do we mean by efficient? Like, how can we guess the efficiency? So the efficiency, the measure of the efficiency is time complexity. Okay, so the measure of efficiency is the time complexity. So how can we say that these two operations are efficient? So these two operations either should be done in order of one time or it should be done in order of log n time. So if we can maintain a data structure in such a way that we can do this thing in order of one time, then definitely we can apply the Mohs algorithm there. Okay, so yes, now these 3 points are the important, these three are the enough, these 3 points are enough to like start with the Mohs algorithm. Okay, so these three, keep these 3 points in a mind, in your mind. Like if you are getting any problem, first you identify the nature of queries. If the nature of the queries is offline queries, then go ahead, then see, like then check the problem, that if you can break down the problem using the square root decomposition idea, and if it is also possible, then look for a data structure. If you can maintain a data structure in which you can like implement these two operations, like a function with these two operations, remove or add, and if you are able to do this, then definitely we can apply the Mohs algorithm. Okay, so now let us understand the Mohs algorithm with a problem statement. Okay, so let me explain you the problem statement. Okay, so the problem statement is similar to the square root decomposition problem which we have, which we took earlier. So what is the problem statement? The problem statement says that you are given an array A of size n. So this A is the array. So we are given an array A of size n. Okay, let me write the problem statement itself. Okay, so what is the problem statement? Given an array A of size n. Okay, and we are given two types of query, not two, only single type of query, and we are given q queries, and in the query we are asked the sum of L to R. Okay, so for this is like very simple problem. There may be many different ways to solve this type of problem, but here we are just understanding the concept of the Mohs algorithm. We would be doing really nice problems using that concept, but if we are taking the hard problem initially, that would be difficult to understand this particular algorithm. So first we are taking a very small problem to do this, but like this is not the very efficient way to solve this type of queries. Okay, but just it is just to understand the problem, the algorithm. Okay, so yes, you are given q queries of this type, sum L to R. Now one can say we can solve it by using naive approach. We can just travel from L to R and we can calculate the sum for that. And in the other ways, what we can do, we can just maintain a prefix sum and just we can do this prefix r minus prefix of l minus 1, and we can just do it in order of 1 time. So for processing q queries we would be requiring order of q times, and we will be done. So this is the most efficient method of doing this. And here the Mohs algorithm we are applying, that is going to take more than this time, like yes, but this is not, the Mohs algorithm is not the perfect solution for this problem, but we are doing this just to understand the nature of the algorithm. Okay, so like don't think that the Mohs algorithm would be the best possible solution for these types of problems. It is just to understanding, for the understanding purpose. Okay. Now, suppose, okay, so now suppose what we were doing, okay, so now let us suppose we are given the array. Consider the problem statement is same. Now suppose we are given an array, okay, and this is our array, and in this array suppose the indices are 0, 1, 2, 3, 4, 5 and 6 and 7 and 8, like these are the indices. Now suppose if we are getting this L2R queries, okay, look, this SL1 to R1 is the first query, SL2 to R2 is the second query, SL3 to R3 is the third query, SL4 to R4 is the fourth query. Okay, if like these are the queries, now what we can do, now suppose like we have to output the result of these queries sequentially. Okay, so suppose if we are like, if the index of this query is 0, the index of this query is 1, if the index of this query is 2, if the index of this query is 3. Now suppose if we are sorting the queries, if we are sorting the queries in such a way that their right end, okay, in such a way that their right end is sorted, okay, this thing is sorted, then what would happen? Let us notice. Okay, now suppose if we are sorting the intervals in such a way that their right limit, their right end is always sorted. Like if say R1 is at this point, then we are definitely sure that R2 is at this point, and the R3 would be at somewhere at this point, and R4 is definitely at this point. Okay, so what I'm saying, we are given these queries and we have to answer these queries. So we are just maintaining the indices of these queries, and we are sorting in such a way that their right limit is always sorted. Okay, their right end is always sorted. So what do we mean by right end? The like rightmost element that is present in the segment. Okay, now suppose if this thing is sorted, now what we can do, we are always sure that if we want to query the result, suppose if we are maintaining the sum as our current sum, so if you want to process the R1 query, then we'll be adding like somewhere L1 would be somewhere at this point, we'll be adding all the elements which falls in this range in our sum, and now R2 is greater than R1, then what would happen? To process this particular segment L2 to R2, we have to always move right, like we have to always sum up these elements. Okay, and suppose if we are summing up these elements, and then L2 falls in somewhere at this point, then we would be decreasing all the elements that falls in between this range L1 to L2. Okay, suppose there is L1 and here we have to L2, then we have to we have to subtract this element, then this element, then this element, and then this element. So that would be storing the result of L2 to R2. Okay, now suppose from here if we have to move to R3, then definitely we have to increase the sum. Okay, and if we are increasing the sum, we will be moving to this R3 point. Okay, so if you observe this thing, now what is happening? Whatever the number of queries, whatever the number of query is, our right end is moving only order of n time. Okay, so what we can say, if we are talking about only the time complexity of this right end. Okay, so right end, if we are only talking about this right end, so what happens with the right end? Right end is continuously increasing for each query. So for whatever may be the number of queries, the the worst case for the right end would be order of n time. But what happens with the left end? Okay, so this is the right end. Now what happens with the left end? So for the left end can move from all the way to the first index to all the way till the last index. Okay, so that is going to cost me like n. So for each query, my L can move all the way from the first point to all the way till the last point. So like for each query, the left can move order of n ways, like order of n time it can take for each to process each query. Because suppose if I am at this point, like suppose if I am drawing my array like this, and suppose if I am at this point, this is my R1 and say this is my R2. Now suppose this is my L1 and this is my L2. In that case, what is going to happen? If I am processing my first query, my L1 is here. Now if I am suppose processing my R2 query, then my L2 is at n minus 1. So it has to move from this point to that point, and then again for some query it has to again move from this point to all the way till 0th index. So this can also be possible. So for each query it is order of n, and for each R2 range we can we have to move our let's say left index n times. So that would be order of n into order of n. So the time complexity here is order of n square. So this doesn't make any difference. Now can we do something better? Okay, so here suppose if these were the queries L1 R1, L2 R2, L3 R3, if these were the queries, then the time complexity to process this query, to move from this query to that query or this query to that query, is the mod of L2 minus L1 and plus the mod of R2 minus R1. So this was the time complexity. Now suppose if I am using the idea, of square root decomposition, if I am using the idea of square root decomposition, and suppose if this was my complete array, now try to understand what I am saying. It would be like a little tough, but it can be useful in lots and lots of problems. Okay, so now suppose if these were the indices, okay, and the square root of 12, the floor value of this would be 3. Okay, so suppose if I am dividing my chunk, so this was my first chunk, this is my second chunk, this is going to be my third chunk, this is going to be my fourth chunk, and this will stand as an individual element. Okay, or you can make a chunk for this also. Okay, so this is my 0th chunk, this is my first chunk, this is my second chunk, and this is my third chunk, and this is my fourth chunk. Now suppose my L, at that point I am sorting R, and my L was freely moving from all the way from 0 to n. Okay, from all the way to 0 to n. So that is costing me order of n square time. Okay, but now suppose if I somehow confine my space, okay, if I reduce my moving space for L, if I am reducing my moving space for L to like for each chunk only, okay, like if moving space for L initially like R was fixed and L is moving all the way from 0th index to nth index, that's why it is costing me order of n square time. But now suppose if somehow I can like restrict my L to move from each chunk only, like move to each chunk only, then what I can achieve is like, for suppose if B is the block size and we have already discussed the optimum size of this B. If B is the block size, the optimum size would be square root of n. Okay. Now suppose if I am like confining my search space in such a way that my L moves only in this particular chunk, then I would be able to achieve this n root n time, like n for each right end and this root n, because the left end can move only in a single chunk. So this would be a better approach. So now what I am doing, so I am sorting, like sorting logic. In the Mohs algorithm, the algorithm only lies in this sorting logic. Okay, this sorting logic is the most important part of the Mohs algorithm. Okay, this thing is the most important part. This is the most important part. How we are going to sort the queries. How we are going to sort queries. So how we are going to sort queries is the most important part here, which here in this Mohs algorithm. So what we are going to do for each query, okay, for each query what we are maintaining, suppose if L to R is my query, I am maintaining the block LB. LB would be the block number in which my left end of the segment lies. Okay, left end of the segment lies. Okay, so now what I am saying, suppose if I am given L1 R1 and L2 R2 and L3 R3 as a query, so what would be LB1? So that would be L1 by SZ. SZ is the size of the block and that is nothing but the square root of n. And LB2 would be L2 by size and LB3 would be L3 by size. Okay, and this size is nothing but the square root of n, which we have already discussed. Now for each query we have maintained this LB. Now what is the LB? LB is the chunk in which the left end of the query is lying. Okay, now suppose now consider only for a single chunk. Okay, only for a single chunk. So now if we are processing only a single chunk, suppose if this was the array and this array was divided in large number of chunks, if this is one chunk, this is the another chunk and this is the last chunk. Okay, now I am considering only this single chunk. Okay, and in this chunk we can have these 3 elements or 4 elements, whatever may be the elements. Okay, now suppose if for this chunk I am sorting my queries, for each chunk I am sorting my queries. Okay, so like I am like, if this is my chunk, I am considering all the queries where this left end lies in this chunk. Okay, like this is the 0 chunk, this is the first chunk and this is the second chunk. Okay, and so, and I am not considering where my right end lies. So this right end can lie anywhere in the array, like at this chunk only also and at this chunk also. I'm just considering my left hand. So if my left hand lies in this particular chunk, I'm going to sort my right hand. Okay, so right hand is always sorted in such a way that R3 would be greater than R2, R2 would be greater than R1 or equals to. Okay, now if in this case, if I am going to move my right hand somehow, suppose if q is the number of queries, okay, and I am processing my right hand. So like first I would be encountering R1. So for R1, my left hand, I am definitely sure that my left hand is going to be present in chunk 0, chunk number 0. Okay, and my R2, after like R, when I am moving from R1 to R2, my L1 would be moving from L1 to L2. Okay, and this L1 and L2, I am pretty sure is lying in this chunk number 0. So for this transaction, what would be the cost of this transaction? Okay, so what would be the cost of this transaction? So suppose if I am moving from L1 L2 to R1 R2, and these both query, and for like okay, L1 R1 to L2 R2, if I am moving from R1 to L2 R2, so I am definitely sure that R2 is greater than R1 because I am sorting my queries in this way only, and I am pretty also sure that this L1 and L2 are present in the same chunk. So the cost for this transition, the cost of this transition would be mod of L1 minus L2 plus mod of R1 minus R2. So the mod of L1 minus L2 would be square root of n, because that is what or you can represent it in this way, because this is the size of the block. Okay, my left hand is confined to this chunk only, and the size of this chunk is only square root of n, so it is confined to square root of n. Okay, for any query, and suppose if I am getting query comparable to n, suppose if q is the number of queries and q is comparable to n, because in most of the cases this is going to happen, that is q is going to be comparable with n. So in that case, whatever be the query number, for all queries, my right hand is definitely going to move from 0 to n only. So the right hand would be n, and for each n query, my left hand is going to move only root n. Okay, so that is going to cost me n root n as a time complexity. Okay, so this is the time complexity I am getting here. Okay, now you can like object that this is only for a single chunk, but we can have many queries in many different chunks because the array is divided into several number of chunks. So now here comes our sorting logic. So we are like, if we are having the queries like L1 R1, L2 R2, L3 R3, L4 R4, or say L5 R5, now I am sorting my queries in such a way that if L1 by Sz is the size, if L1, okay, let me write it more clearly. So I am sorting it in such a way that if L and R are coming, so I am sorting it in such a way that if like this is my query number A and if this is my query number B, so if L1 by Sz is less than is equals to L2 by Sz, if this is the condition, like if the block number to which the left hand lies is same, then I am sorting on the basis of right hand, not the right block. Here this is the left block, but this is the right end. So if then I am sorting it on the basis of right end. Okay, if this is the case, I am sorting it on the basis of this, and if it is not the case, I am going to sort it on the basis of the block number. Okay, so any doubts in the sorting logic? Anyone in the comment section? like first what we are doing, for each query we are dividing the left hand into some number of block, and if so first we are sorting on the basis of the block number of the left limit, and if the block number of the left limit is same, then we are going to sort it on the basis of the right hand. Okay, anyone having any doubts, like please mention in the comment section like how we are sorting. So like if we write the pseudocode for this, if we write this pseudocode for this, then if suppose A is my one query and B is my another query, then and if say LA and LB is the block number of the left hand, then if LA is not equals to LB, then I will be returning on the basis of the right hand, like what would be the say A dot right or B dot right, and if it is equal, then I will be like, okay, if it is not equal, then I am going to sort it on the basis of their left hand only, okay, left block number only. So that would be LA is less than LB, and if it is not the case, I am going to sort it on the basis of LA and LB only. Okay, sorry, then I am going to sort it on the basis of right hand. So that would be A dot R, B dot R. Okay, anyone having any doubts in this? This is our sorting logic, how we are going to sort the queries. So you can understand this sorting as the sorting of the vector pairs. First we are looking to the block number of the left limit, and then we are sorting on the basis of the right hand. Okay, so as I am not getting any doubts, I think this is clear to all. Okay, now let us analyze the time complexity of the complete operation. Okay, so what is going to be the time complexity of the complete operation? So suppose if you are having this q queries, okay, and this q is always comparable to n, so I am considering this q is always comparable to n. Okay, now for processing each query, we are going to process the right hand and we are going to process the left hand. So for each block, my right hand can move all the way to n, like from 0 to n minus 1. So it can move all the way to n, and for the left hand, as the left hand is confined to only one chunk, so it would only going to move to the square, like the maximum the movement it can achieve is square root of n. So that is going to be the say queries, like for each query, this is going to be the movement of the left hand for each query. Now what could be the maximum number of queries if we are considering this left hand? So if we are considering a single chunk, the maximum number of queries we can answer would be this block size only, okay, because in worst case what can happen is, like all the queries are present in the different, like this is L1, this is L2, this is L3. If this is the case, you would be having the root n queries. Okay, so for answering the root n queries, you would be having the root n into root n here and plus n, because the number of queries doesn't matter here. You can move right hand all the way from 0 to n minus 1. Okay, now if you are getting n queries and you have already processed, like each block is processing root n queries, so what is the total number of queries per block? So that would be n into root n. So you have to multiply it using by n into root n. Okay, so if you multiply it with this thing, you are going to get n root n plus n root n as your query. Okay, so this comes out to be 2 root n and 2 n root n, and this is the time complexity. Okay, or you can just write it as order of n root n. So this is the time complexity. Okay, so this is the Mohs algorithm. So this is all about the time complexity of the Mohs algorithm. Okay, now let us try to map the things we have discussed earlier with a problem statement. So what is the problem statement that is given to us? We are given an array A of size n, and we are given q queries, and we have to process these queries, and all the queries of type sum L to R, like we have to sum all the elements that falls in the range L to R. Okay, so this is what we have to do. Now what were the requirements? So the requirements is where we have discussed the requirements. So these were the requirements. So are the queries in the problem are offline? Yes, definitely it is offline, because we are only getting the one type of queries, sum L to R, and this we can process all the queries first, and then we can print the result for each query, and we will be getting the results. Definitely this is offline queries. So this condition is satisfied. Now can we use the square root decomposition? We have already discussed that how we are going to use the square root decomposition in this query. Okay, and the another thing is maintaining a data structure. Can we maintain a data structure in such a way that we can implement the add and remove function? So let us try to do that also. Okay, so for that we would be maintaining a data structure that is, say, int. Okay, int sum is the data structure. This is the data structure which would do the job. Okay, so for example, sum is storing the sum of some elements. Okay, it is storing the sum of some elements of the array. Now we can call the add function, and suppose if this is the array and the sum is storing the sum of this particular portion. Okay, now suppose if we want to add the sum of this element also, we can just, like if this element is a of I, we can just add up sum plus equals to a of I, and this is my add function. We can just do this, and this is my data structure. And for removing, suppose if we are removing this particular element, that is a of j, we can just subtract it from the sum. The sum of minus equals to a of j, and that would be doing my remove operation. So yes, we can maintain a data structure that is just an integer variable, and we can implement these two operations on this, that is add operation and the remove operation, and we can just solve this problem. Okay, because for each operation in the add operation we have to include that element, and for including that element you can just sum it up, and for removing that element you can just subtract the value of that element from the sum. So this would satisfy the third condition also, so that we can say that we can apply this algorithm, this Mohs algorithm here. Now I have to solve one problem, but as we are not having much time to solve that problem, so we would be just implementing the data structure only. Okay, we'll be solving the problem in the later lecture, but here we are going to implement the data structure only. Okay, implementing the algorithm, more precisely implementing the algorithms. Now for that, what we need a data structure that we have already discussed. That would be only a that is only an integer variable. We'll be having an add function that would be adding some element, a single element in my range, a remove function which would be removing a single element from my range, and most important function, that is the comparator function. A comparator function to sort the queries, and a structure. Okay, so the structure to store the query. So these are the 5 functions we have to maintain to implement the query. Okay. So let us take a look at implementation also. Someone is saying that, sir, implementation mat karo. Okay, but like I am just giving you the idea how we are going to implement the data structure. We are not going to solve the problems, so just for the idea purpose. Okay, or we can do that also in the, say, upcoming class. So just like in this lecture we can just see how we can solve the problem by taking an example, and we'll be implementing in the next lecture, implementing everything in the next lecture. Okay, so let us take an example. Okay, now suppose if we are given an array, if this is the array, and suppose these are the indices 0 1 2 3 4 5 6 7 8 and 9, and suppose the elements are 2 4 1 3 5 7 6 9 10 11. Okay, and suppose if we are also doing the chunks, so these are the chunks. These are the chunks. Okay, and now suppose if I am getting 4 queries, or say 3 queries only, and the query are sum 2 to 5, sum 0 to 7, sum say 5 to 8. Now the first thing we are going to do is we are going to sort it on the basis of our logic. So suppose if we are searching the left block for each one, so the size of the square root of this would be square root of 9, that is 3, and this is nothing but the size of the block, and LB is just the left limit by the size of the block. Okay, so 2 by 3 is nothing but 0. Okay, 0 by 3 is also nothing but 0, and 5 by 3 is nothing but 1. Okay, now these are my right limits. So as the left limit for these two are same, I am going to sort it on the basis of these two values. So I am going to get the sorting same. Okay, like the sorting result would be same, 2 to 5 and then 0 to 7, and then as this is the LB here is 1, then I am going to get this query. Okay, 5 of 8. Or to understand it more clearly, what we can do is we can just swap these two queries. Okay, you can write sum of 2 to 5 here and the sum of 0 to 7 here. Okay, now sorry, it should be sum of say 0 to 7 here and 2 to 5 here. Okay, now if you are sorting this, as this right limit, as this left limit is same for these two values, then we are going to sort it on the basis of the right limit. So first this is going to come first, and this is going to move to the second value. Okay, so initially I have already taken the sorted value, so in that case you won't understand. Okay, so that's why I have swapped these two queries. and then this query is going to move at this point. Now what we are going to do, initially both the pointers would be at this point at the -1. Okay, and what I would be doing, like if I am processing the first query, what I would be doing, I am going to, like, this is my sum variable, which is my data structure, in which I am going to add an element or delete an element. So what I am going to do is I am going to apply an add operation. Okay, so first I am having this add and remove operation. First I am going to apply an add operation, and I am going to add this 2 here. Then I am going to apply again an add operation, and I am going to add 4 here. Then I am going to apply a add operation, and I am going to have a 1 here. Then again I am going to have a 3 here, and I have to move unless I am reaching at this point. Okay, so then again I am going to have this 5 here, and then again I am going to have this 7 here, and after this I would be at this point and I don't have to consider this. Okay, then I will check if my left limit is at the perfect point or not. So it is not at the perfect point because it is at the -1th index, and I have to move it to the second index. So if I am increasing my L, then I have to call the remove operation. So I will call a remove operation for this element, so it would be subtracting 2, and then I have to call a remove operation for this, and it would be subtracting 4. Okay, and then I am at this point, and this I have to include, so I won't be doing anything. Okay, so this is for the first query. Then for the second query, now if I am processing my second query, so for second query, so this is say sum 1 and this is say sum 2. So sum 2 would be sum 1 plus sum 1 plus, now I have to like apply a add operation for this, so I would be adding 6, and I am applying again a add operation, so I have to add this, and now my right limit would be at this point, and this would exceed the right end of the segment. Okay, so now I have to move my left point. So as my left point is here, I have to move it all the way till this point. So I have to again apply an add operation, that would be +1, not +1 because it is already added, but I have to move it here and I have to add it. So I have to add +4 and I have to add again +2. Okay, so in the similar way this would be sum 2, and next we are going to do for sum 3. So for sum 3, it is going to be sum 2, and then I have to, my right end is at this point, this point, because I have already processed this one, and as this is in my right hand limit, I am going to increase this. Okay, so that would be sum 2 plus 8, and then I have to move all the way my left pointer from this 0th index to all the way till this 4th index, and I have to subtract all these values. I have to call the remove function for this for these 5 elements. So that would be -2, -4, -1, -3, -5. Okay, and if we are going to calculate this value, so that is 2 plus 4 is 6, 6 plus 1 7, 7 plus 3 10, 10 plus 5 15, 15 plus 7 is 22, and this 22 minus 2 is 20, and this 20 minus 4 is 16. So this is going to be 16, and 16 is my this value. Then 16 plus 6 is again 22, and 22 plus 9 is again 31, 35 and 37. So this is going to be 37, and this is my 37. So that would be 37 plus 8 would be 45, minus 2 would be 43, minus 4 would be 39, minus 1 would be 38, and minus 3 would be 35, minus 5 would be 30. So that comes out to be 30, and we can match the result, and we would be getting these, like this result only. So this is the stimulation of our algorithm. This is the stimulation of algorithm, how our algorithm is going to run. So this is all for today. We are going to like implement it in the further lectures. So thank you.